In single quantum, we make the world's most sensitive single photon detectors, only limited by the law of physics. That's our motto, that's what we want to achieve. And I think we're doing quite a good job on that. And it is, of course, very interesting to see that these devices can also be transferred into other fields. And that's why we're contributing here to this project of SuperMama. Literally, what's cool about it is that the sensor we're making, they need to be cooled to about 3 Kelvin, that they work very sensitively. And that is because they are made from superconducting material, very thin, only 10 nanometers thick. And then we etch a meander out of it on the order of like 100 nanometers. And we send a current through just before the critical current breaks down. So these devices become very sensitive to all kind of energy which is deposited on that superconductor. If this has enough energy to break the Cooper pairs, there is a quantum phase change, and the superconductor becomes resistive, and you can measure an electronic click. And now the energy can be deposited, what we usually use in our business, by photons, but also this energy can be delivered by electrons, X-rays, or as in SuperMama by atoms and molecules.
Ci sono diversi vantaggi a operare questi circuiti a temperatura criogenica. Uno dei maggiori vantaggi è il fatto che il rumore è ridotto, e poi ci sono altre prestazioni che sono migliorate, come per esempio anche il consumo di potenza, che è ridotto in modo drastico. Principalmente il progettare circuiti che siano prevedibili nelle prestazioni, e cioè che si possano in un qualche modo modellizzare a priori in modo tale che poi durante l'utilizzo funzionino in modo, come dire, prevedibile, in modo aspettato. Noi crediamo che un sistema integrato di supporto ai rivelatori consenta di raggiungere livelli di complessità maggiore, una maggiore scalabilità e specialmente una compattezza superiore. E di conseguenza abbiamo sempre richiamato l'attenzione degli altri ricercatori sul fatto che l'utilizzo di questi circuiti elettronici a temperatura criogenica vicini ai rivelatori possa avere dei vantaggi notevoli.
Du coup, on profite lorsque les circuits sont en très basse température. Premièrement, le niveau de bruit est très bas, vu que la température est aussi basse. Et deuxièmement, on a besoin de beaucoup moins de power et d'énergie pour avoir des grands niveaux de signal. So, le plus grand challenge, c'est que normalement, lorsqu'on fait un design de circuit électronique, on a besoin de modèles pour faire des simulations avant de fabriquer le circuit. Mais dans notre cas, vu qu'on travaille en très basse température, il n'y a pas assez de modèles dans les technologies sur lesquelles on travaille. Du coup, on doit nous-mêmes faire les modèles et nous-mêmes tester le circuit.
We are building tiny silicon electronic chips that are used to read out and control the superconducting nanowires that our partners build, and that have to work at really low temperatures. So that's the cool part of our work. So we really need to push the performance envelope of what we are designing and then testing. We are an academic institution, so we need to stay also at the forefront of the research. So that's certainly one part of the coolness. And the other part is that we like to explore new ideas and basically to boldly go where no electron has gone before. Yeah, cold for us is really super freezingly cold, even colder than in Switzerland. So it's minus 270, more or less, give and take, which is the temperature of liquid helium. There is specialized equipment that has been built and perfected over the years. So right now, it is still costly, but much less than it used to be. So the chips need to be that cold for 2 reasons. So A is performance. When we reduce the temperature, then we can go faster. We can read out faster. We dissipate less power, which is very important. The chips are less noisy, which means that we can read much smaller signals. And the second, equally important, if not more, reason is that we want to co-integrate our chips with the sensors. So we want to put them really close together, maybe one day even stack them, which is the contrary of what is mostly done today, where the whole electronics sits in big racks outside of the fridges that host the sensors.